Yo, Grant, what is this, bro?
This?
Yeah, what is this?
Oh, it's the new John QTrain. It's just like underground jazz artist. I found him on SoundCloud.
John QTrain?
Yeah.
Bro, this sounds like
John QTrain, an AI jazz musician that can improvise a melody in real time over a harmony. We've realized that jazz can be reduced to a Markov decision process with only a significant amount of assumptions. John QTrain is a recurrent neural network that approximates the Q function of this MDP. He is trained on MIDI data from some of the best jazz standards of all time. Jazz improvisation embodies decision-making under uncertainty because musicians must listen to each other and make real-time decisions about what note, tempo, and volume to play without any reference to a composition.
There have been multiple prior attempts at an AI jazz musician, but they have yet to achieve a subjective quality that consistently matches human performance. One example used a transformer to model jazz lead sheets, and another example used a recurrent neural network to implement a jazz accompanist. Our approach consisted of 3 parts: data processing, model design, and model training. For data processing, we first found a dataset on Kaggle called Jazz ML Ready MIDI. Then we selected 30 songs from them that were structurally simple and extracted their lead and backup tracks. In the end, we had 30 populated song objects that were ready to be processed by our model. Our problem can be formulated as a Markov decision process with the following states, actions, and rewards. The state was all previous notes played by the lead and backup. The action is a vector in range 0 to 129, which represents a note played at the current time step. And the reward is the quality of the played note. We formulated our MDP as a recurrent neural network, which consisted of several parts. First was an input pre-processing layer that represented the prediction for the key at the current time step. Next, we passed the state and key into an LSTM, which we decided to use because of the linear temporal nature of music. After this, we passed it to a final linear layer, which would output a vector in the size of the action space. The output of the model was the Q values for the input current state, and we used a softmax function to produce a sampled action.
For training the model, we took inspiration from the Q-learning paradigm, but with a machine learning twist. The loss function we were minimizing was the mean squared error of the Q-learning objective. At each time step, we would feed one music interval into the model to compute the Q vector for all possible actions. Then we would consider only the Q value for the action that was actually taken in the training set, and compute the loss between that value and the reward plus the discounted maximum value of the output of the model's next time step. We did not use Monte Carlo sampling, and instead computed the mean squared error for the entire song before taking giant steps with the gradient. The reward function that was used during training is a mixture of 4 components. The velocity reward, which assumes louder notes in the training data were better notes, a closeness reward, which incentivizes consecutive notes that are closer together, a chord reward, which incentivizes lead notes that are present in the harmony, and a scale reward, which incentivizes lead notes that are part of the song's key.
Next, I will go over the results of our model. We were able to decrease the training loss of John QTrain from 3.44, which was a randomized model, to 2.13, which was our final model. We were also able to achieve a testing loss of 2.95, which shows that the model was not overfit on the training data. We also evaluated our model subjectively and found that it had a solid performance. We were able to improve this subjective quality by tweaking hyperparameters and retraining the model. For training, we decreased the discount, increased the reward for closeness, and increased the reward for playing in key. For evaluating, we decreased the temperature for softmax and increased the scale lock.
Ultimately, John QTrain was able to successfully learn melodic jazz improvisation through Q-learning. Here are a few key decisions that were the most influential toward its resulting performance. Firstly, we decided to discretize all notes to eighth notes so the state space was a tractable size. However, restricting the model to play in eighth notes took away some of the human feel that naturally exists in jazz. Secondly, our decision to use an RNN for the Q function was key to allowing it to understand the temporal relationships in jazz music. However, modeling jazz as an MDP inherently assumes an objective truth in what makes good jazz music. Finally, our iterative approach to designing the reward function, as well as tuning that function in our sampling procedures using hyperparameters, ultimately gave us far more success than relying fully on the model to learn the underlying structure of jazz music. This human-in-the-loop approach, creating John QTrain, ultimately gave us an improviser that was not very good, but was surprisingly competent, despite the small model and dataset.
For future work, we want to improve our reward model by making it more robust in its quantification. We also want to expand for more training data so that the model has different examples and a breadth of musical backgrounds to pull from. And lastly, we want to incorporate negative training examples so the model can also learn what not to do. In conclusion, we created an AI jazz musician that was able to improvise a melody using Q learning and a Markov decision process. Check it out!